In this presentation, I will be presenting Aura 3D, Overlap Region Aware Multiview 3D Object Detection. A landmark work in the camera-only multiview 3D object detection task is Deter 3D. It introduces a promising multi-view detection pipeline that processes 6 images concurrently in an end-to-end manner, predicting all objects around simultaneously and implicitly utilizing rich information in the overlapping regions. Even though Deter 3D performs reasonably well, we found that the network, without explicit guidance, does not totally use the geometric potentials of multi-view camera systems. Specifically, the network's understanding of the scene could be limited to that of a monocular detection network, resulting in multiple false positives in the overlapped regions. Thus, how to deal with this issue to boost detection accuracy remains a crucial problem. As reported by Chen, Disparity Supervision, which fully pilots the network by exploiting the strong association of binocular images, substantially improves detection performance. Inspired by this observation, we propose to use stereo disparity estimation techniques on the overlap region, which is between all adjacent camera pairs in the surround view setting. Although this region is relatively small, it serves as a geometric link between two images. Consequently, we apply outputs from the traditional stereo disparity estimation model as weak depth supervision to improve the detection accuracy over the overlap region. We empirically found that this supervision significantly improves the overall detection accuracy. This is only part of a story. Unlike the human vision system that quickly identifies an object across overlapped cameras, we empirically observe that deep neural network has a strong inductive bias toward identifying objects individually in each single view image. This often results in failing to utilize additional information of the same instance appearing in other different view images. Moreover, we observe a domain shift effect between the overlap region and the non-overlap region due to camera lens distortion. To find the degree of inductive bias, we visualize the TSNE results of central, which is non-overlapped, and edge, which is overlapped regions features. As we clearly see in the first row, which is Deter 3D, the features of each two groups form distinguishable clusters. Our method starts with this observation. The overlap regions in multi-view images are clues to improving the overall performance. Ultimately, the features of our method's two groups are distributed harmoniously, minimizing bias. This distribution indicates that our proposed method successfully minimizes the representational gap. We propose to train an adversarial overlap region discriminator, which minimizes the domain gap between objects in the non-overlap regions versus overlap regions. We validate from experiments that such adversarial training makes the overlap region performance more robust. We start from the state-of-the-art multi-view 3D object detection model called Deter 3D. Our model takes multi-view camera inputs and outputs a set of 3D bounding boxes for objects in the scene. Built upon Deter 3D, our model consists of two main modules. First, stereo disparity estimation for weak supervision. Our depth estimation head is trained to predict a dense depth map of the overlap region. Second, adversarial overlap region discriminator, which minimizes the gap between non-overlap regions versus overlap regions, improves the overall detection performance. We evaluate the effectiveness of our proposed method using the New Scenes dataset, which is a widely used large-scale multi-view 3D object detection benchmark. Through comprehensive experiments, we verify that our proposed model generally outperforms the state-of-the-art approaches in the camera-only 3D object detection task. Our main contribution is listed as follows. First, we report that existing works often neglect properly dealing with objects in the overlap region, which limits fully using the geometric potentials of multi-view camera systems, causing performance degradation. Second, we propose to use outputs from the traditional stereo disparity estimation model on the overlap region and apply them as weak supervision to improve the detection accuracy over the overlap region. We empirically find that this supervision significantly improves the overall detection accuracy. Finally, we introduce an overlap region discriminator that adversarially learns to minimize the covariate shift between objects from non-overlap regions versus from overlap regions. In this section, we present a method to effectively utilize such small but highly informative area. When considering the multi-view camera system, adjacent cameras have a strong association. We regard this association comes from overlap regions and can be extended to geometric guides. To interactively supervise the network, we train the stereo disparity estimation head, which reconstructs a dense disparity map with overlap region pairs of neighboring cameras. We follow the recent work by Liu to implement the disparity estimation head. Our stereo network extracts features of an image pair with a standard visual encoder. Our disparity estimation head outputs a cost volume through multiscale stereo matching. To obtain the target disparity map, We use the output from the conventional stereo matching algorithm, which performs pixel-wise mutual information-based matching. Note that our disparity estimation module is supervised only for the overlapped areas, but we empirically show that it significantly improves the network's overall 3D object detection performance. Note also that our disparity estimation head can be disabled during evaluation and testing to improve computational efficiency. We use a standard stereofocal loss on disparity estimation from a pair of overlapped images. Using the output of the stereo matching algorithm as a weak supervision, we optimize the following stereofocal loss to train our stereo disparity estimation head. We use a binary mask to consider losses from overlap regions, blocking gradients from non-overlap regions for training our stereo disparity estimation module. Given the known internal camera parameters and external parameters, we first map the point in the source image coordinate to the point in the world coordinate. Then, we project the point back to the point in the target, or neighboring, camera coordinate frame. Empirically, we discovered that DNN-based multi-view object detection models have a strong inductive bias toward identifying objects individually in each image. Note that objects in the overlap region are often occluded mainly due to limited field of view of the camera or suffer from deformation due to camera lens distortion. Finally, we observe a domain shift effect between the overlap region and non-overlap region. In addition to leveraging stereo disparity information, which gives an implicit bias to process the same object in different view images together, we propose to use a regularizer to explicitly minimize the representational gap between non-overlap regions versus overlap regions. Specifically, we constrain the object detection head from learning region invariant information via an adversarial framework using gradient reversal layer. Notably, to reduce inductive bias, we design this ordinary discriminator as a special. We intentionally make a loss negative, preventing the discriminator from rightly distinguishing. Finally, our network is robust to all areas, minimizing bias that boosts performance degradation for overlapped regions. Formally, a region discriminator needs to predict its source region correctly. Thus, this classifier is trained using region classification loss as follows. Ultimately, our model is trained end-to-end by minimizing the following loss function, where lambda CLS, lambda box, lambda D, and lambda R are hyperparameters that are drawn from a grid search to control the strength of each loss. We compare our proposed Aura 3D with existing state-of-the-art methods including CenterNet, FCAS 3D, PGD, DD3D, Deter 3D, and BEVDET. The first four approaches take multiple single-view images independently and combine detection outputs for the final output using non-maximum suppression. The last two approaches, Deter 3D and BEVDET, are state-of-the-art multi-view 3D object detection models. As shown in Table 1A and B, Aura 3D generally outperforms other methods in terms of NDS and map both in validation and test data. Note that FCOS 3D uses test time augmentation and a customized data augmentation strategy, thus requiring more epochs and model ensembles. Though we do not use such an augmentation strategy, ours performs better than these methods. Note that we initialize with DD3D pre-trained model and use the same backbone for a fair comparison with Deter 3D and BEVDET. Further, we observe in Table 2 that ours show higher MAP scores in all objects except the trailer. Note that ours is initialized from the same backbone of Deter 3D. This confirms that our proposed regularization terms clearly improve the overall detection performance. We compare our proposed Aura 3D again with existing state-of-the-art methods, FCAS 3D, and Deter 3D, but we now focus on overlap regions. As shown in Table 3, our method outperforms FCAS 3D and Deter 3D in terms of all metrics except MASE and MAAE. This confirms that our overlap region-aware approach effectively deals with objects in the overlap region, resulting in a large performance gain. For a fair comparison, all models use a ResNet 101-based backbone, and only FCAS 3D uses an augmentation strategy. We evaluate the variance of our method with Deter 3D with and without the following two main loss terms, stereo disparity estimation loss, and adversarial overlap region discrimination loss. In Table 4, we quantitatively analyze the importance of our proposed methods for the whole region and the overlap region. Note that we use the new scenes mini-validation set. In Table 4 whole region, we observe that adding either LD improves most of the metrics, while a similar trend is observed by adding LR as well. Indeed, the stereo disparity loss is reflected during training to induce semantic geometric potentials evenly in all areas without distinguishing between overlap and non-overlap regions. In Table 4 overlap region, the effect of each component on the overlap region is further confirmed. Most importantly, we discover the remarkable efficiency of LR in the target domain. The adversarial loss completely addresses the domain shift effect by deceiving the model into not correctly discriminating which region objects belong to. As a result, we confirmed that our components improve overall performance. Existing CNN-based methods benefit from inductive bias even with relatively small datasets. However, large-scale datasets have become more common, and in these environments, inductive bias easily overfits specific datasets and causes various domain shift issues. In this section, we demonstrate that our proposed methods address these concerns while maximizing the capacity of multi-view camera systems. This figure shows the visualized results of 3D bounding boxes predicted by Deter 3D with green boxes and our proposed method with pink boxes. The ground truth bounding boxes with blue boxes are overlaid. We project the predicted and ground truth bounding boxes in the BEV perspective. In general, Deter 3D and our proposed method generate reasonable results. However, the difference in the overlap region is apparent between the two methods, where Deter 3D exhibits a relatively large number of false positive detections. Especially, our model is more robust for truncated or distorted objects across the entire region. Overall, our simple and effective methods amplify accuracy both qualitatively and quantitatively. Thank you for listening.